Okay, let's get started. So on Monday, we talked about making a WebSocket connection. Today we're going to talk about what do we do after we make that connection. Before we get started, are there any open questions? Anything out there that needs to be addressed? All right, go into lecture mode. So last time we created this connection. Oh, the lights. So last time we created the connection. Now we're going to start sending messages. What do we do with those messages? How do we communicate via WebSockets? So we want to talk about all day today. And this is the end of the WebSocket content. These two lectures is everything you need to know about WebSockets. And then on Friday, I'm going to go over examples. I'm going to show you WebSockets in action, show you some code, show you some actual WebSocket frames, and really solidify how we're parsing these and what the protocol is. But after today, you'll be able to do objectives 1 and 2 on the homework. So this is a WebSocket frame. This is what we're going to talk about all day today, is what all of this information means. We're going to look at every single piece of this and talk about what it all means. This is what you'll have to parse when you get a WebSocket frame, which is how WebSocket messages are communicated. When you get a frame, how do you handle that? And this is everything you need to know about frames. We're going to piece it all apart. So first, I want to quickly kind of recap protocols. We've talked about protocols earlier in the semester, but let's solidify this now that you have to parse your own protocol. That's not HTTP. HTTP has a more flexible structure, I'll say, where WebSockets are these bytes have to have this information in it. This is the first really rigid protocol that you've seen that you have to parse. So protocols are a way to make sense of the ones and zeros that we send over the internet. So we send these ones and zeros. That's the only thing the internet can communicate. And the protocols say how we're going to interpret those ones and zeros. As long as the client and server both agree on the protocol and follow it exactly, then we're going to be able to effectively communicate. So we saw IP, our first protocol, the protocol of the internet, how everything over the internet is communicated. With IP, this is how routers can figure out where an internet packet should go, how to get it to its destination IP. And we saw TCP, which is once it makes it to its destination IP, how does a packet get interpreted by that device? So TCP is handling things like port numbers, different processes listening on different ports, and also packet, the sequence number of packets to be able to reassemble a packet. If the message that you're trying to send, whatever you're sending over the internet, is too large for a single IP packet, then TCP is going to assemble those multiple packets and get the entire message. So we took these two for granted. We just said, these work. If you want to learn more about them, take modern networking concepts. We're not going to touch them in this class. But now we're talking about WebSockets. We're going to follow the same structures, the same idea, same format. The RFC, they like using this format. And I ain't arguing. I like the format. I think it's fairly straightforward, at least once you get used to it. But this is the format that we're going to follow. So now we're going to have to learn how to read this format and what all this information means. But when this packet is sent over the internet, this is what a packet's going to look like, assuming for a WebSocket frame, assuming that everything can fit in a single packet. So when the ones and zeros are flying over the internet, it's going to be the IP headers, followed by the TCP headers, followed by the WebSocket headers, and finally the WebSocket payload, the actual information that we want to send. But all of this information is going to be sent in a very specific order over the internet. And the routers of the internet, they're going to read the IP headers, figure out where this thing's going to go. Once it makes it to its destination device, the IP headers are no longer used, and that device is going to read the TCP headers to reassemble multiple packets if needed, and send this information, send its payload to the appropriate port. We're going to send it to the appropriate port, which is the process that's listening on that port. And then the TCP packets are no longer needed. And then finally, when we get to our program at the application level, we're going to start reading this WebSocket protocol, just like we used to have HTTP down here. The WebSocket headers and payload are going to be down here. Technically, this data isn't here. The data is the WebSocket protocol. I should have overlapped that. But this is how information is set over the internet. So if you want to send a WebSocket packet to somebody, this is what it's going to actually look like when it's flying through the wires and fiber of the internet. So let's talk about parsing these things. The IP, TCP did their thing. We get this packet. We get this information, this frame, and we have to parse it. So I want to take a brief talk about parsing bits. This is where we're finally getting into bit level parsing. We're getting at the lowest level that as programmers we have access to anyway. Lowest level of information being communicated, individual bits. So I want to talk about what bit parsing is, just hopefully just a refresher, but what this is going to be. So it's helpful to remember that when you have bytes, and whenever you're reading from your TCP stream, you have a stream of bytes. We're sending bytes. We've talked about bytes a lot this semester. So we already are familiar with bytes. And bytes are 8-bit integer values. We know that bytes are 8 bits, but the important keyword there is integer in most languages. So if you take a byte and print it to a screen, in most languages it's going to be printed as a decimal number. So it looks like it's an int. It looks like an integer value in decimal form, but we need to remember that that actually is an 8-bit representation underneath. It's just 8 ones and zeros. But when you handle it in your language, it's going to seem like it's a decimal number just because the language is trying to make it human readable. So now that we want to parse those bits, we have to kind of peel back that layer of human readability and get into those 8 bits. So for example, if we have an int value, or an integer value, which is a byte for 8 bits, an 8-bit integer value, and we want to get, say, just the last 4 values of that byte. So for example, the first byte of this information, these are each individual bits. So the first byte is going to be this fin bit, these 3 reserve bits, and the opcode. So when you read the very first byte of this information, of this frame, you get all of this information. If say you're only interested in the opcode, and we'll talk about what all these things are once we talk about parsing bits. If you're only interested in the opcode, what you can do is take the first byte of the frame and it, a bitwise and, which is just a single ampersand in most languages. That's why you have to have 2 ampersands for logical and. Bitwise and is already claimed a single ampersand. So single ampersand, bitwise and it with what we call a bit mask of, in this case, 15. So if we bitwise and whatever value the first byte is with 15, which is 1111 in binary, this effectively zeroes out the 4 higher order bits and just returns the 4 lower order bits. Now we have a value from 0 to 15, which is going to represent our opcode. And we can do this further. We can mask out individual bits. If we want to just read that 4th least significant bit, we can AND it with 0000100 or 8, right? I hope I didn't mess that one up. Or 8 and get just that individual bit. If you AND it with 8 and the result is 8, then that bit was 1. If the result is 0, that bit was 0. So hopefully all this is refresher from 191, 341 if you took that already. Probably several other classes. I think you talk about this in 220 a decent amount at least, especially with representing doubles and things like that. So hopefully this is review. But it's possible. Do any of those courses make you code any of that? Or is it all like written on paper? Okay. So that's going to be the new thing, taking this and applying it to your code. That's the new thing you get to do in this class, which is exciting to me because, like I said before when I first mentioned bit parsing, you learn all that stuff in the other classes, but you never use it. Like, it's one of those why do I care kind of things. Well, here's a case where we actually have to care. You actually have to know this stuff and apply it to your code, which I always get excited about. Like, good, that class wasn't a waste. So hopefully you feel the same. All right, so let's go through any questions on this, by the way. All right, let's go through these frames and talk about what each one of these values represents. So, did I skip one already? Yeah. So let's just go through these one at a time. I'll give you a heads up. These the first entire byte, we're not going to have to worry too much about. We're going to talk about what they are. The opcode you might have to worry about a little bit. I'll talk about that. But when we get to payload length, that's where the action happens. So first, the finish bit. This is the very first bit of the frame. It's either 1 if this is the last frame of the message, or 0 if it's not, if there are more frames that are going to come. This is, for our purposes, we're just going to assume that this is always 1. That will almost certainly be the case in all of your testing for your homework and all of the grading. I don't know of a case where it wouldn't be 1, but just hedging my bets a little bit, and I'll say almost always. The reason for this bit's existence is if you're using WebSockets as a stream, if you're streaming data over over WebSockets, you might want to say, hey, 0, this is not the last bit. I have more information for you. It's just not ready yet. When we talk about payload length, we'll see that one single WebSocket frame can send a ridiculous amount of data. There's effectively no limit to the size of a frame. So this wouldn't be like buffering, or not buffering. This wouldn't be like if you want to send a very large file in a WebSocket frame or a huge amount of data. You would still have a finished bit of 1, but you would have a finished bit of 0 if the data just isn't available. Maybe you're streaming video and you want to send what you have and say, hey, finished bit is 0 because I still got more data that I'm waiting on. I just want you to have partial information here so you can start processing on your end. So in most cases, we're going to see 1 for that, unless we have very specific applications, which we won't in this class, that require a finished bit of 0. So we're going to assume 1. Reserve bits, we're going to assume these are 0, 0, 0. Reserve bits 1, 2, and 3 for a 3-bit reserve code. We're not going to use these. These are built into the protocol to attempt to future-proof WebSockets. So if another protocol comes along that wants to be built on top of the WebSocket protocol, so still using that WebSocket handshake, but then using something else for the rest of the frames, then they can use these reserve bits. So if there's another protocol somebody wants to come up with, they're going to set these reserve bits to something else and say, as a way of saying, I'm either using this different protocol or I'm adding these different options to WebSockets. Refer to this RFC for information about that or whatever. We're going to use just plain old WebSockets with no opcodes, no reserve bits. So you're going to assume that these are always 0, 0, 0, and they will be. The browser's not going to set these just on a whim or anything. You would have to really intentionally have these set. And then opcode, or operation code, this is going to specify the type of information in the WebSocket frame. For our purposes, we're going to assume it's 0001 for text on the homework. But if you wanted to send binary information, say you wanted to send images over a WebSocket frame, you would change this opcode to 2 instead of 1. And if you see an opcode of 8, that means close the connection. This is the one that you'll actually see. I'll allow you to assume it's just 1 for the homework. But if you do see an opcode of 8, you might see this in your testing. It does happen every once in a while. If you see an opcode of 8 and your server crashes, that probably means you didn't parse the opcode of 8. You tried to handle that as a regular WebSocket frame. So your server might crash on the 8s. You might want to add some robustness to your server to make sure it doesn't crash on opcodes of 8. But I'm going to allow you to assume that it's 1. An opcode of 8, closing the connection, you're going to see this if you close a tab. You're going to get that opcode of 8 because the browser is saying, hey, this connection's done. My user just said we're done with this WebSocket, and then send that opcode of 8. So that one you might see in your testing, even though I'm allowing you to assume text only. All right, let's start getting into the good stuff. The mask bit, the mask itself, and the payload length, That's going to be the bulk of the work that you do on Objective 2. So this we're going to spend like the rest of lecture on. So the mask bit, either 1 if mask is being used, 0 if a mask is not being used. Pretty straightforward. Most of the conversation about this is when we talk about what the mask actually is and what it does. Which I'm going to go in order of the bits here. So we're going to save that conversation for after we get done with payload lengths. But if this mask is 1, then these 4 bytes are going to be the mask. And if this is 0, these 4 bytes won't exist. We'll go right from payload length right into the data, the payload data. So that mask bit tells us whether these 4 bytes exist or not, or if we go right to the payload data. And if they exist, we have to handle those masks, those 4 bytes. Frame length. This is probably the one that will require the most work. It's not an absurd amount of work, but there are some tricks, and it does test your binary and byte knowledge and integer knowledge, transferring everything, transferring it into different bits and bytes. So the content length, the payload length, is similar to content length. The payload length is going to at least be this 7 bits. So these 7 bits, only 7, so you're going to have to read the byte, zero out the mask bit, so you can give this a mask of 127. Yeah, 127. I always hate having to come up with those on the spot. I always have that doubt, like, did you say the wrong number? So you would AND that byte with 127 to zero out the mask bit, and then just get the 7 least significant bits of the byte, and then that's your original payload length. Now this payload length might have more bytes to it. So if the payload is less than 126 bytes, so if it's not 126, it's not 127, then we know it's less than 126, and in that case, that's your payload length. That's it. All these other bytes don't exist, and you're going right to the masking key or the payload data if the mask bit is 0. So there's some flexibility in these bytes. These bytes don't always exist. If the payload length, this 7-bit payload length, is less than 126, that's the length of the payload. End of story. That's very limiting if that's the only thing the protocol does. So if the length of the payload is greater than 126, or 126 bits or greater, we need ways to represent that. So if the payload length is greater than or equal to 126, but less than 64K, then that 7-bit payload length will be exactly 126. So if you read those 7 bits, and those 7 bits are exactly 126, 7 ones and a 0, I don't feel like saying them all, then this is your payload length. Your payload length is somewhere in between these 2 values, and the next 16 bits, the next 2 bytes, so this information right here, these 2 bytes, are going to be your actual payload length. So if the payload length, the 7-bit payload length is exactly 126, that's a way for the protocol to tell you, hey, I needed 2 bytes to represent the payload length. Read the next 2 bytes, and that's your actual payload length. The 126 is just a heads up. Hey, I needed more than 7 bits to represent the payload length. Read the next 2 bytes, that's your payload length. If the payload length is more than 64K, then the 7 bits will be exactly 127, all ones. So if this is all ones, your payload length is going to be the next 64 bits. The next 8 bytes are going to be the payload length. And this is where we have a little future proofing in WebSockets. The next 8 bytes, all of this, is going to be the payload length. 8 bytes. That means we have a maximum payload length of 16 exabytes, which is 16 million terabytes. They're really trying to future-proof this, and who knows, there might be a day where that's irrelevant, where that's a ridiculously small amount of data. Who knows? But for our purposes, for the modern world, the current state of the world, it's pretty future-proof. These WebSocket frames can get absurdly large. I mean, just sending this much data over the internet, the load on the network and everything, that's absurd. It's an absurd amount of data, which is good. I like seeing that stuff because, like the mistake, I won't say mistake, but like with IPv4, when it sounded like a lot of IP addresses, several billion, but then we ran out because that's not even close to meeting our needs now. We need way more than several billion IP addresses. So with WebSockets, I said, you know what? Whatever we think is going to be the maximum we'll ever need, let's multiply that by a couple million, by several billion or whatever. So the payload can be absolutely enormous. Now the good news for your homework anyway, we're not going to send any payload that's more than 1K. So you're never going to see a length with the first 7 bits being 127. You're just not going to see that. I considered it for this semester. Maybe next semester I will. But it's just a bit much for the homework. You would have to get into buffering on your TCPs like we did on homework 2. And I already hit you with buffering. I don't need to retest your buffering. I already, if you got it, if you got to homework 3, you already got through buffering. Making you do it again, I don't know. I just didn't see the value in it for the extra confusion and trouble that it would cause. But maybe someday. So you'd have to do WebSockets with buffering. I guess that's all it would add, right? Just the buffering. I could probably add it next semester. But you're off the hook for this semester because I put it in the testing notes that we won't test with more than 1K. So you can read all in one read from your TCP socket. So you get the whole frame in one go. Or else you'd have to do the same thing we did with content length. You would read the payload length and then keep buffering until you read that many bytes. Payload length is in bytes, by the way. Oh yeah, I say that all over, bytes. So that's payload length. You read the first 7 bits. Those 7 bits will always exist. You read these 7 bits. If it's less than 126, that's your payload length, and you go right to the masking key or the payload data. The masking bit, by the way, is always going to be 1 when you're reading packets. So you're going to go to the masking bit when you're parsing. If the payload length is 126 exactly, then the next 2 bytes will be the actual payload length. And after those 2 bytes, we'll jump right to the masking key, which will be right up here. If the payload length is exactly 127, the next 8 bytes will be the actual payload length. All of this will be the payload length. And then the masking bits. So for your homework, you will have to check, is that exactly 126 or less than 126? And if it is exactly 126, there is, things get a little bit tricky here. You have 2 bytes. You're going to read 2 individual bytes, and you have to combine them to be 1 integer. So it gets a little bit tricky, too. And the reason we go up to 1K is you will have to read at least a few bits from that most significant byte. All right, any questions on payload length? And again, like most things in this field anyway, this is one thing that's probably pretty straightforward to consume on the slides. Like I don't think I lost anybody there, maybe on some of the smaller details, but it's pretty straightforward to see on the slides. It's when you go to code it up. Like you have to 100% understand what I'm saying on the slide. So when you code it up, you're not making mistakes. Because when you go to code it, it's not gonna feel as easy as it does on the slides. which is why I have a whole lecture on Friday about examples in the code. All right, so let's revisit this masking. We're done with all this payload stuff, and we got to the masking key. So let's talk about this masking key. If the mask bit is 1, that key exists. These 4 bytes after the payload length are going to be the masking key. If it's 0, we go right to payload data. I'll get a little bit ahead of my slides here. If you're receiving a packet, if you're receiving a WebSocket frame, the masking bit's going to be 1. If you're sending a WebSocket frame, masking bit's going to be 0, and there's going to be no mask. So you're receiving masked data, you're sending unmasked data. So just a little foreshadow on why we need to talk about this. So when the mask bit is 1, so when the frames that you're going to parse that are sent by the client, the mask bit's going to be 1, and these 4 bytes will be the masking key. These 4 bytes are XORed with each 4 bytes of the payload data. So the payload data is not just the raw bytes of the payload. They're the bytes of the payload XORed with these 4 bytes, and 4 bytes at a time. So these first 4 bytes of payload data are XORed with the masking key. The next 4 bytes of the data are also XORed with the masking key, next 4 bytes, et cetera, all throughout the entire payload length. And if the payload is not divisible by 4, and whatever extra bytes are just masked with the first however many bytes we need of the masking key. So if there's an extra like 3 bytes at the end, you'll use the first 3 bytes of the masking key to XOR with those 3 bytes. Why not just send the raw bytes? We'll answer that. Well, the short answer is caching, to avoid caching. But I'll have that in a slide also. Good question. So if the 4 bytes that we want to send are these bytes, say 4 bytes of the message, this will just be part of the message. But for those 4 bytes of the message, maybe these are the first 4 bytes. If these are the first 4 bytes of the message, we're going to generate some random mask, or the browser is going to generate some random mask, and we'll just say the random mask is this. It's just going to be random 1s and 0s. So we're going to XOR this message with the mask. So XOR 0, 0, 1, bitwise XOR 1, 0, and we get this. This is the payload, those 4 bytes of payload, XORed with the mask. When we receive the bytes, we're going to XOR them with the mask again. And when we XOR them with the mask again, we're going to get back to our original message. So if we take this and XOR it with the random mask, 0, 1, 0, 0, we're going to get exactly the original message. This is effectively the message and then the mask XORed with itself. Anything XORed with itself is just straight 0s. So we're effectively XORing this with all 0s. If we mask it twice. So we get the mask data and we effectively unmask it by XORing it with the mask again. So we're undoing the masking. So when we receive the payload, each 4 bytes will unmask, and then actually read the payload message. And for a coding tip, I don't recommend actually XORing it 4 bytes at a time. Iterate through the payload data, the indices of the payload data. Take the indice, mod it by 4, and then go to your whatever data structure you're storing the masking bytes in, and then get the index based on that, modded by 4. You have index 0, modded by 4 will be 0. Get the 0th bit of the masking key. The second byte, index 1, XOR it with 1, etc. The 5th one, XOR it with 4. It's going to give you 1. Get the first, 5. The 5th one is right here. Index 5, XOR it with 4, or mod it with 4. That'll give you 1, which will be this byte. of the masking key. That's what I recommend doing in your program. Don't try to do it in chunks of 4, because then when you get to the last part of the payload, you have to have if I have 1 byte, if I have 2 bytes, if I have 3 bytes, if I have 4 bytes, and have different code for each one of those cases. Just go byte by byte and figure out which byte of the masking key you need based on the index of that byte that you're unmasking. Makes things a lot cleaner in the code. When we want to send a message to the client, we use the same exact format. There's no request response. There's no differences like that. When we send WebSocket frames, either whether they're being sent from the client, sent from the server, same exact protocol. So between parsing and writing frames, very little difference. There's a little bit of practical difference in the masking bit, and that's it. The only difference is you're not using a mask. When you're, did I pass my slide where I talk about caching? Maybe I did. I don't know. But so I'll just say it off slide then. When we're sending from the client to the server, we want to use that masking bit to avoid caching. Say a user wants to send the same message to your server multiple times. We don't want those messages to look identical, because then if we have some aggressive caching happening at some point, those messages might get cached. So we want to avoid caching, so we're going to use this masking just to scramble up the data. So even sending the same message multiple times, it's always going to be completely different. It's going to look very, very different with high probability. With 1/2 to the, I gotta stop doing my powers of 2 off the top of my head like that. Very high probability you're going to have different messages. 2 to the 32. We don't have those same concerns when sending something from the server to the client. The browser shouldn't be receiving a message from a server and then just using a cached, it just doesn't quite make sense on the browser side. On the server side, we want to optimize that. If a client's sending a message, the million clients are sending messages, we might not want to go through our entire logic of our program to get the message, the response. If it's something we've seen a million times, we're just going to send them the cached response. We want to break that when receiving messages from the client, but sending from the server to the client, it's fine, no worries. So don't use a masking bit. This should be 0, and your masking key won't exist. You'll go right to the payload data after payload length. So, a recap of some of the assumptions in homework 1. Fin bit will be 1, reserve bits will be 0, opcode will be 1. So the first byte that you read, you can assume is always 129. This is probably this is what I would recommend as the first thing that you do. Even though you can always assume it's 129, make sure it's 129. Read that first byte and check its value, check what it is. If it's not 129, you're not even ready to start parsing these frames. You want to make sure that that's 129, because if it's not 129, you got something wrong somewhere in your server. So I would use this as a kind of a sanity check. Send a WebSocket frame from the browser. Have your WebSocket connection stuff, obviously after Objective 1 and the connection is made, have some form, ship some data over that WebSocket, and make sure the first byte that you're reading is actually 6 zeros and then a 1. If it is, then you're ready to start reading the payload length, checking its value, seeing how many bytes you need to read for payload length, going into the masking key, and doing all that good stuff. But this is your first sanity check. Is that 129 in the first byte? If yes, then you're looking good. And then you're going to check the length of the information you want to send, formulate your payload length. You'll have some length. This is the message that I want to send from the server. Convert that into your 7-bit payload length and potentially the next 2 bytes. So you're just reversing the process that you just did on the parsing side. And then add the payload data and then ship it. Now, one of the requirements, so there used to be a little bit of cheese in this, where you would just take the WebSocket frame that the browser constructed and reuse all the payload length. That won't work because you do have to escape, because you're just taking chat messages and sending them to everybody. But you do have to escape your HTML. So we're going to be looking for this on the grading side. We're going to send you some messages with a bunch of HTML in them, and then making sure that you're actually computing the payload length in the packets that you send. So when we send you HTML, you have to escape it. One character just turned into 4 characters, or 5 in the case of ampersands. So you do actually have to, that's my way of forcing you to compute the payload length. So just a heads up on that. There's no cheese in it. Because you would get away with that until we start throwing HTML at you. And you should be testing with HTML as well, making sure that's escaped. So when you're sending frames, masking bit 0. After payload length, go right to payload data. Got that. Any questions on any of this? This is my last slide. No questions in chat. Any questions on any of this? This is everything for Objective 2. This is everything for WebSockets. Yes? It's to avoid caching. Is that your question? It's to prevent caching. We don't want caching here at all. So the masking bit is making sure that everything's so different that, no matter what Nginx or Apache or whatever else is in between our app and the user, that at no step of the way, or the browser, that no step of the way, nobody's going to be caching anything. Because if we're getting these payload messages, like think of our chat app, we don't want anything to be cached because we want to make sure that that information makes it all the way to our app. So we can know that this user sent us a message. We need to add that to our database. We need to process this, store it, send it to other users. We need to have a lot of processing that our app needs to do. So we don't want anything in the middle saying, oh, I just saw this request. Nginx maybe says, oh, I just saw a request that looks exactly like this. Even though it's not even a request. They might interpret it as an HTTP request or whatever. I'm not going to tell the app about this. I'm just going to send whatever the app sent last time I saw this, looking at Nginx's caches. We don't want anything doing that. We want to make sure our app sees every message in these WebSocket frames. So we have this mask. The browser's going to add this mask and all this stuff just to make sure it looks so different that no one's caching. Because it's not like for example, an HTTP request for your index.html. That can easily be cached. The browser doesn't have to care every time somebody accesses our static content. All of our HTML or CSS or JavaScript, that can be cached at any level along the way, and we're fine with that. But with this, we don't want any of this being cached. And there are some very aggressive, like caching is really nice for optimization. There's a lot of really nice caching stuff going on. But this is a case where we're like, no, don't get fancy with us. We want this information. Anything else? Maybe we'll end a little early, and then on Friday I'll give examples. We'll go to the code and start playing around with some WebSockets. See y'all Friday.